Welcome to the glass plate. In this example we're going to do once more a steady state conduction of heat in a one-dimensional strip. The strip runs from x equals 0 to L and is insulated everywhere except for left and right. Well, that's to say, this is kept at temperature T0 and this one also is insulated. So my insulation now runs almost everywhere. No heat can pass through these. Heat flow can only go out at the right hand side. To make it even a little bit more challenging, I'm going to assume that there is heat production per unit volume here, but it's no longer a constant. This is a function of position. And it's linearly decreasing, so most heat per unit volume is produced here and nothing there. And the question again that we would like to address and get answered, what is now the temperature profile in this system? And once you have that, how much heat is coming out? Alright, let's see what we need to do. We need to set up a balance, that's for sure. It's a heat balance. Also for sure, steady state heat conduction. If you want to find the profile, you better make use of the microbalances. So for this control volume, I'm going to evaluate steady state balancing. And the ins and outs are, as we always have for the conduction cases, Fourier's law. And the same at x plus dx. And now the production in this volume is the production per unit volume times how big our volume is, A dx. Can turn this quickly, like we did before, into a differential equation. Scratch out the a's, divide by dx and divide by lambda, and you get the d dx of the function dt dx equals minus q123 over lambda. This looks pretty much like an earlier example where I had fixed the two temperatures, but it's not the same. And I need to sharpen up my notation to remind me that it's not the same, because what is different is not only the boundaries, but this is a function of x. And that changes this differential equation. So I better make that explicit. Now we see what we need to do. We need to integrate left and right to change from the derivative of the derivative to only dt dx. So the left part is as we done before, and it's going to give us dt dx. The right hand side is integrating this part. That's a linear function that I need to integrate, and I know how to do that. The 1 turns into an x, the x turns into x squared, half x squared actually, and I should not forget the integration constant C1. I need to integrate this once more to get the temperature distribution. But before doing so, it is always a good idea to think about, can we find C1 out of a boundary condition or can't we? Depends on the problem. What are the boundary conditions in this case? On the right hand side, fixed temperature. On the left hand side, there is no heat flowing out. So this is forbidden. What does that mean? If there is no heat flowing out, then this term must be identical to 0 on this spot, so not at any x, but exactly at that x. It must be. Lambda is not 0, the a is not 0, so this means that dt dx at x equals 0 is identical to 0. Now nothing can flow in or out. Oh, but if I use that at x equals 0, this is a 0, so this boundary condition goes in immediately here. 0 equals 0 minus 0, so this term is 0 plus C1. Ha, big deal. C1 is 0. That simplifies life, because now I only need to integrate this part. So t of x equals integrating again on that side. I integrate x to x squared over 2. I integrate x squared to x cubed. An additional 3 below, so 2 times 3 is a 6, plus an integration constant c2. Boundary condition, I sure got one left on that side. X equals L, out of that follows t equals 0. Out of that follows c2 equals, substitute it for yourself, it's just a matter of filling in. Once you have that, you can substitute everything in t, x, and get it worked out. Okay, once you have the temperature profile, you can compute how much heat goes out. But the only place where heat can come out here is on the right, because everything is insulated. So you're going to find how much heat is flowing out, but I don't know. There's another way of finding. I don't need to stick to a micro balance to find out the temperature distribution and then the heat coming out. I could choose a more clever control volume. And I can do so. Let me re-sketch quickly, but now smaller. Everything here was insulated, and only heat can be flowing out here. So here's an outflow, phi sub q out. All right, if I use this control volume and I set up my steady state heat balance, then nothing flows in, phi q out comes out, and the total production is everything produced here. So Q out is readily solved here if I find what is that production. Oh, but that production is what you produce in this one, plus in this one, plus in that one. So it is per slab between x and x plus dx, exactly what we wrote here. Q triple A dx. Now I have this one. But I need to add that one, and so on. That means that I basically have to integrate from left, x equals 0, to right, L. And this can be written in, where is my relation for the production? Q0 triple is a constant, can be taken out of the integral. And then I have 1 minus x, and a can be taken out. This a 1 minus x over L, dx from 0 to L. And that's going to be a q0, 1, 2, 3 times integrate this one, gives me x minus x squared over L to L between 0 and L. This gives me 1L. The 0 doesn't do anything. This gives me L squared over L and a half, so a half L, and the 0 doesn't do anything. So this gives me a half A L Q03. Check for yourself whether your answer that you backed out here, if you put in Fourier's law and try and calculate how much heat flows on the right hand side, that you arrive at this value. It should. Good luck!